event then. My pleasure to introduce Dr. Ian Faluna, who is a biomicrometeorologist and a professor in the Department of Land, Air, and Water Resources, the Air Quality Research Center, and the Agricultural Experiment Station at the University of California at Davis. Ian originally studied physical chemistry at UC Santa Cruz, including summer research in computational chemistry at Los Alamos National Lab, and then earned his PhD in meteorology at Penn State. For 4 years in between this, he worked in industry as an air quality consultant for Secor Incorporated in Fort Collins, Colorado, running dispersion models and making measurements of industrial emissions. Later, after a postdoctoral appointment with the Advanced Study Program at the National Center for Atmospheric Research, NCAR, in Boulder, Colorado, he joined the Atmospheric Science faculty at UC Davis. Ian's research interests include the airborne investigation of entrainment and turbulent dispersion, observational trace gas emission estimates, public interest research, background ozone, and the influences of synoptic to microscale meteorology on atmospheric photochemistry. Today, he's here to speak to us about his research on the relative contributions from different sources of that most pernicious atmospheric pollutant, ozone, which of course is always of great concern right here in the Phoenix area. And a lot of his research has actually happened in Southern Arizona, which makes this talk, I think, particularly relevant to all of us. And he'll be talking about the implications of his research for future measurements, modeling, and regulatory standards related to air pollution. So the title of his talk is Soils, Wildfires, and Background Ozone, the Rise of a New Air Quality Photochemical Regime. Please, let's all welcome Dr. Ian Faluna.
All right. Thank you so much for having me. Thank you, Steve, for that introduction. I can't tell you how much fun I'm having here. A devilishly good time. I saw a guy on an airplane recently. I know, hiss. I saw with a shirt that said "Dad joke loading" with a little bar waiting, and I thought I'd take that as a call to arms, so I'd inject as many dad jokes as I possibly could. So, as Steve mentioned, we were talking recently when he was visiting Davis, and I wanted to share this with you, this work that we've done on some of the ozone, the network of ozone monitors that are across the nation about air pollution and how it's changing its shape and its features as we enter, or as we, careen into the Anthropocene, and how we're going to have to think about it differently. And so I wanted to talk specifically about agricultural sources and how they affect our chemistry, wildfires, which of course are really becoming dominant. And this, I tried to get some visual representation of the ozone in the stratosphere. Most of the ozone, 90% of the ozone is in the stratospheric layer, around 25 kilometers. And it is responsible for that deep blue you see in the late evenings. So you do have this a visual connection to our the bulk of our stratospheric ozone, which I want to talk about today. So I'd like to first, start with trying to motivate, why is it important? Why is air quality important? Why is ozone important? And if you look at the global killers, environmental killers of humans, you have something estimates of, these air bars are pretty large, but the estimates of the air pollution that they prematurely kill almost 6 million people every year. So of course, we now all have a COVID sort of, what does that number mean? We know that COVID killed something like 2 million a year for a couple of years. And so we have a sense of how significant this is as an ongoing problem of air pollution. If you look a little closer to home, estimates in the US show that air pollution prematurely kills a few 100,000 in the US. California, about a tenth of that, which is a little better than the proportion of the population in California, but most of those are attributed to particulate matter. So I'm not really going to talk too much about particulate matter, but it's usually called PM, just so you know. And it is really important, and ozone is really at the heart of the chemistry of the atmosphere. I'm going to call this the atmosphere that we live in, where most of the weather occurs. I'm going to call it the troposphere, the technical term. This lower sort of 80 to 90% of the mass of the atmosphere that's very sort of dynamically quite active. And these particles are produced through chemistry reactions and a lot of them are mediated by the amount of ozone. So ozone's a real sort of central player in our air quality. So it's much smaller number as far as we understand are contributing to ozone to the public health crisis, but it is central to all the chemistry. It's also toxic to plants, so it's known to reduce crop yields, and it's also, in fact, known to impact carbon uptake in the biosphere. So it can have impacts and be coupled to other global environmental issues. And of course, it's the third largest or most powerful anthropogenic greenhouse gas in terms of net effect. If you look at sort of an IPCC map, that third bar there it's only 10 to 15% weaker than methane. So the CO2, methane, and then this lower, not the stratospheric ozone, but the lower tropospheric ozone has an impact on our climate through the radiation. Now, getting closer to what your day-to-day experience is like, American Lung Association puts out the state of the air every year. And you can see here we have it. You've got this area as number 5. I mean, fortunately for me, being in California, the top 4 are all in my backyard. So I'm hopefully have job security for a bit. But you can see that Phoenix, despite it not being the 5th most, well, is it the 5th most populous city? It is actually, yeah. But it's way above Houston, which is actually more populous, right? 4th. Anyways, the point is that Phoenix has a surprising, pretty poor grade as far as ozone is concerned. And then if you look at particulate matter, which again has a lot of the direct health impacts, it's still in the top 10. So you guys have air quality issues that are still quite pertinent and germane. So the US, the way this is started to be done in the early 70s of the US EPA was established. They created the Clean Air Act, and the way it's regulated is by requiring that air across the country fall below certain thresholds, like speed limits of pollutant levels. And these are known as collectively as the National Ambient Air Quality Standards. And since the early 70s, when the Clean Air Act first started, we've seen great improvements in a lot of the main pollutants that this was concerned with. The remaining 2 that are still problematic, however, is ozone and particulate matter. So I'm going to focus on those. So this is a most recent map of the US EPA's ascertainment of who is above and below that threshold. And you can see, of course, that we have your home here in this yellow patch. And of course, California is still, we're number 1. So there's lots and lots of work to do yet. And so I've been thinking a lot about particularly the Southwest and why some of these cities have these urban areas have these very persistent air pollution problems. And I want to get to that. But just to get some of the jargon out of the way, ozone is regulated by something called a mean, it's called an MDA8, which is a running 8-hour average. It's the maximum of that average every 24-hour period, every day. So that's what we consider to be the standard by which we have to measure whether you're in compliance or not. And that's because of an exposure level. We used to be a spike in ozone, a 1-hour average, but it's this integrated longer term average that we think is most important to human health impacts. And the compliance comes down to something it's called an ozone design value, which is it's an extreme value statistics where they're looking at approximately the 98th percentile and above of ozone days. So the idea is you get like 3 mulligans a year where you can have as high ozone as you want, but that 4th one, that's going to determine your design value. And that's approximately, 99 percentile, actually. 98, if you think about it, it only is half a year. So that's how we measure it, this extreme value statistic. And I'm going to be talking about this ozone design value a lot because in a regulatory sense, that's important. And what we really care about is not so much the average ozone, but rather these extreme events. So I want to keep that in mind because it's important to understand how it differs from the mean. Okay, and so just to give you some bearing in terms of Maricopa County, you are considered moderate currently. So it means your design value, that 4th highest, is somewhere between 81 and 93 parts per billion, which is just a mole fraction concentration of ozone in air. Okay, and anyways, if there are any questions that are going to block you from understanding anything, please feel free to pop them up now so we can just understand everything as we go. So to give you just a general background of what this ozone looks like, this tropospheric ozone. Again, there's a natural stratospheric layer. We know about that. This was the topic of was it our last environmental crisis? I would say our last big environmental crisis after acid rain. We had this stratospheric ozone problem. And so that is a normal amount that we know shields us from harmful UV radiation at the surface. And some of it gets mixed down into the lower part of the atmosphere, the troposphere. Like I said, where most of the weather and the activity and most human exposure occurs. And so there's a lot of work on ozone that involves a lot of detailed chemistry. And that's all what most modelers will really focus on. Most atmospheric chemists are really trying to understand all of the complex chemistry that goes into the production of ozone. So there's a natural source, but then there's also this, what we call anthropogenic, this human-induced production that happens. And you need a little ozone to get the whole thing started. But humans emit things that in turn make a bunch of ozone and amplifies the problem. And so this is generally what's considered to be urban ozone pollution, has to do with these emissions. And it's complicated because it comes from biogenic sources, agricultural sources, industrial sources. And the two main things I want you to understand about this, without knowing all of the detailed chemistry, is that we have this thing called hydrocarbons. This is called volatile organic carbon, these VOCs. That's a whole huge field, right, of organic chemistry. They're in the air. They're helping to produce ozone, but they're just the one component with NOx, which is the other compound that's important, which is NO and NO2. So the X is like a algebraic variable that can be 1 or 2, collectively known as NOx because they interconvert rapidly in the atmosphere. So you need these nitrogen oxides and you need these VOCs, and there's complicated chemistry, but that makes OH. I'm sorry, that makes ozone. Sorry about that. All right, so that's the main focus. But if you take a step back for a minute and think about the background ozone, it's really interesting. It comes down to a few main terms. And these are kind of depicted by these average values I put here on the right with a standard deviation of an ensemble of models of like 23 global models that they compare these things to. And when you boil it down, there's a lot of production, there's a lot of loss. And again, this is stimulated by human activity. And in the net, the difference between production and loss is about 400 of these units. The dry deposition, which is just ozone hitting surfaces and reacting away, getting removed by physical deposition at the surface, is about 1,000 of those units. And the natural input from the stratosphere is about 600. So in a global sense, it's really stratospheric source, deposition at the surface, and that sets up a vertical gradient in the background. But then we have these local places where there's emissions of VOCs and NOx, which complicate that issue. So this is a picture of a NASA model for a few days. Now, this is the ozone season, the Northern Hemisphere. So this is starting in July, and it's ticking through. And I just wanted to show you this to give you a sense. Now, this is just a model, so we're not sure if this is exactly accurate, but what the surface level ozone looks like as day and night comes and goes throughout the warm season when there's a lot of that photochemical productions happening from those VOCs and the NOx, and particularly concentrated in urban areas, yeah? You can see that LA pulse. But it requires actinic radiation. It requires sunlight to get this chemistry going to produce the ozone. So you see this big pulsing, it depends on the time of day. And anyone who's ever looked at ozone data over time knows that it peaks in the afternoon. And of course, that's a high exposure time for people who work outside. Anyways, this is just fun to look at. I always like to give these nice visuals for people who are totally disinterested. Just so that's the general picture that we have in a full-blown chemical transport model. That's sort of the top of what we can do. This is just to give you a sense of the main players. I just told you about the main terms in the budget in the ozone, tropospheric ozone level. And these are estimates we made of just some main terms in that budget. So convective mixing, it's kind of ad hoc, it doesn't matter. It's relatively quick. This troposphere, it's called tropo, is overturning. So it's a part of the atmosphere that's overturning. So mixing in the vertical is relatively effective. If you look at advection in our mid-latitudes, that goes from west to east, and the westerlies that blow around the globe, we see that the advection is long. It takes a long time down low, but as you get up higher and the winds are faster, that shortens. And then these are some estimates of photochemistry. And the thing to realize about the ozone photochemistry is its main loss is getting photolyzed, but then that photolysis product, that excited oxygen atom, has to react with water to be lost. Otherwise, it just reacts with molecular oxygen and reforms ozone. So the loss of ozone is strongly linked to the amount of water in the atmosphere, which, if you've ever studied the atmosphere, is a huge gradient in water as you go up because of just the thermodynamic lid of the Clausius-Clapeyron equation. Right? At some point, you start creating clouds. There's only so much water vapor that can exist. Because the temperature drops off, that falls off exponentially with height. Bless you. All right, so the photochemistry means that and the presence of water, that loss of ozone, the photochemical lifetime changes from several days in the near surface, maybe a week or two, up to over a year in the upper troposphere. So where you are as an ozone molecule in the atmosphere strongly depends on where you're going to get to and what you can do in the meantime. So this is probably a little TMI, but no matter where you go, you keep finding, if you look at profiles of ozone in the background troposphere, again, away from big cities and so forth, you see a remarkably consistent picture that is in line with this idea that there's a natural source from the stratosphere. This requires large-scale atmospheric storm systems to come by, sweep through, and mix down air from the stratosphere into the troposphere. And there's this constant loss at the surface. And there's all this complicated chemistry along the way. But generally speaking, this background leads to a pretty clean, well-established gradient in the background troposphere. So this is a fascinating study. I know there's a lot here. I'm going to zoom in just a second. But this gives us an idea of, this is from reanalysis data, just meteorological data, in terms of stratospheric air that makes it to the surface, or makes it actually into the troposphere. And these are different levels in the troposphere on the left. So the higher up you are, that's mid-troposphere. You can see there's more stratospheric air making it to that level. And as you get lower and lower towards the surface, there's less and less of that making it down there. That's all makes some sense. But it's this data on the right that I find incredibly fascinating, and particularly the spring and the summer. And these are instances of what they call deep stratosphere to troposphere exchange events. And this is averaged over these seasons. Let me just focus in on that. What do you see here in the spring? Where's the big bullseye? Yeah, oh, I think I can see your house. It's right there in that red patch, right? And then it's only matched by the Tibetan Plateau, where you have this these dry, part of this has a lot to do with this atmospheric mixing. You heat the surface, heats the air near the surface, that becomes incredibly buoyant, less dense than the surrounding air, and rapidly rises. This is convection. This convection over these desert areas where a lot of that energy from the sun does not go into evaporating water, because there is none, very little, then all of that energy goes into creating less dense air and these rising deep thermals, which is why you get sometimes the afternoon thunderstorms in the monsoon, because they rise so high, they get cold enough to condense and form cloud and precipitation. And it's rivaled only really by the Tibetan Plateau, which is also a desert, but it starts very much higher than us. But you have these very deep mixing. And what that means is that air from the upper troposphere that's been injected from the stratosphere is able to be mixed down to the surface. So you have this coupling between the stratosphere, really, and the surface. And it's particularly acute where we are. And even, this is spring, so people have known about this for a long time, but even in the summer months, you still have these deep blue patches. And so you do have this mixing, and this is, I think, is really underappreciated in terms of how most people think about air quality, because I'm going to argue that that is the dominant reason that we have not seen improvements in ozone in the Southwest in about a decade. So this is a simulation I found from NASA of one of these events. So this is just a few days, this model. So this is a 70 parts per billion isosurface, which is high up in the top of the troposphere. And you're seeing how I just wanted to show you this to give you a sense of how the dynamics of the atmosphere act to make this motion. And this occurs around storm cyclonic events of weather systems that are propagating across the Pacific. And because the stratosphere and the upper troposphere is so stable, statically stable, it requires work. It requires a fair bit of this, what we call synoptic energy of a storm system to pull that air down, because it's so much less dense than the air below it. But you do get these events that then pull these sheets of stratospheric air, which are very dry and also very high ozone, then they get draped across the Southwest. Okay, so colleagues, let's see, how am I doing? Okay, so colleagues of mine, Dave Parrish and Dick Derwent, started looking at this background and started thinking about it in a more simplistic way than usually involving all this chemical transport modeling, trying to get every single VOC in there and all the NOx and get it all right. We started thinking about, let's move away from these big urban sources and try to look at the background ozone and how it's behaving. So this is an example on the left of the ozone trace from Mace Head, which is at the western edge of Ireland. So it's got in the westerlies across the Atlantic Ocean. It's considered like a background site. There's not much anthropogenic human stuff upwind of that. And these are different ozone climatologies I've done in different, for about a decade of different colors. And it goes from the 80s to 90s, 90s to aughts in the purple, and then aughts to 2016 in the blue. So what you can see is this annual cycle, which we understand it peaks where this is that peak in that ozone introduction from the stratosphere, those storms that pull down stratospheric air. So you have this peak in this is again a boundary layer in the ocean, marine boundary layer air peaks there, but you can see that annual cycle is actually changing over time. And so this is a compilation of 13 of these background sites across the northern hemisphere, mid-latitudes. And we find this sort of general behavior of this sort of parabolic arc, that the ozone in the background atmosphere seems to have been going up in the late 20th century, somewhere around 2005, 2010, peaked, and then has been coming down ever since. And this is not, turns out this is controversial to say this, because computer models don't say that. Even though I'm surprised, that corresponds fairly well with when China reached its max NOx emissions, which everyone believes, as you can verify with satellite, was around 2011, 2010, 2011. So we think this is consistent with sort of this background also being influenced by human emissions, but having a trajectory, having a change, having a temporal or a secular trend, which is important to keep in mind, because I'm going to argue soon that this is the dominant term of ozone in the Southwest. So just to cast a little bit of shade at my modeling friends, because it's very easy to get enthralled with a model and get so much complexity that believe it has to represent something closer to truth than the very simple analysis I'm going to show you here. This is a comparison between the models. These are European in the Alps, high altitude sites, which are considered to be background away from sort of direct anthropogenic emissions. And you see those open symbols are what the models predicted in terms of the last sort of half century of change. And this is what the observations show. They show a different trend throughout the 20th century, and actually like an absolute difference of something like 10 parts per billion, whatever that is, 20%. Now, this is where the mean comes in interesting, because if we're going to talk about air pollution, we talk about the ozone design value, these high ozone events. And that is a extreme statistic. So the mean is not exactly what you want to think about. So here's a modeling study I found that used two different chemical transport models, which is the red and the blue. And then they showed the distributions at 12 different background sites across the Southwest, where we're talking about here. And the black line is the observation, the distribution of the observation at those 12 sites in the summertime, spring to early summer. And what you'll see here then is the model can also estimate what the background is doing, and that's what the dashed lines are. But I just wanted to draw your eye to the point that while the means may be within 5 to 10 parts per billion, which is what we understand models to be able to get sort of in terms of their accuracy, notice the wings are very different. What we care about for air pollution is those high values. And models are notoriously not great at getting those high values. So you can see the distinction. If you can eyeball kind of a 99th percentile out there, you can see that the two different models give drastically different extreme values. And so this is what we're trying to call the attention to of the modeling community, to say that we have a lot of work to do in terms of capturing this accurately. So the method we developed was pretty simple-minded. It was pretty like first-year calculus or analytical geometry in high school. You want to get a curve. We thought, look, we know that there's this background that's going up and going down. We get it from the measurements of background sites. Well, we also know that air pollution has been improving because of regulatory efforts across the country and the globe, really. But we'll focus on the US here from here on. And so we said, well, let's assume that there's this parabolic background, which we fit pretty accurately from all our measurements, and then also assume that there's an exponential decay on top of that, and just fit a function. Is that up there in the right? This is what the ozone design value should be doing over these decadal timescales. And so that's a simple curve fit that can be done. We know the B and C terms from the background measurements. And then the capital A and the tau we've seen from all these sites across the US. We know that the tau is remarkably consistent at about 22 years is an E-folding time of anthropogenic ozone. So we put that in there, and we only then solve for lowercase a, which is the background level, and this capital A. And they're all quantified to the year 2000, just so, of course, everything's changing in time. So we had that there. This is an example that actually included an Arizona site in Yuma. I just wanted to show you here. This is also a region I've been doing a lot of work in the Salton Sea area, which feels similar to this, this place here. Last July, I was driving a trailer full of equipment back, and I had to pull over when it became 118, and I thought for sure the wheels were gonna melt. So you're familiar with the kind of heat that they experience down there. And they also had this similar problem, that there's this ozone that's persistent. It's not decreasing anymore. This exponential decay has played itself out. The regulatory efforts are no longer paying dividends. So this plot on the right is the plot of an isoplethe of those A values. This is the background. And when I say background, I don't mean necessarily like the tropospheric background, like those pictures I was telling you about. That's part of it. But the other part is anything that's not being regulated. Anything that's not experiencing this exponential decay due to improvements in most of this is coming from fleet improvements. Our internal combustion engines are becoming more efficient, low emissions. And so this is what's improving these things. Anything that's not there doing that is part of this background, this lowercase a. And look at, lo and behold, what pops out of this simple-minded analysis from the observational data only, without a complex chemical transport model, is you find these regions that are incredibly impacted by this background ozone. And in the Coachella Valley, Palm Springs in the south, and also in the Imperial Valley down near the border with Calexico and Mexicali, you see these very high levels of the background. 70, turns out 70 is that threshold I was telling you about, the National Ambient Air Quality Standard. So the point is, we're not gonna do much better than that, because right along we have this background, which is there, so something's going on. San Joaquin Valley, another whole hot mess that I'll talk about some other time, and I'm invited back. Sacramento plume also, where I live. So there's a lot to do, and we think it's also linked to agriculture. So I'll get to that in a second. So one other thing we all know is that wildfires are becoming much more prevalent and impactful. And so we got cocky. We started thinking, wow, this gave us all this really interesting information from this simple parametric fit of these functions. Let's put in a line that estimates wildfire estimates. And it turns out wildfires are, we can pretty cleanly, well, it's crude. This is all crude, but you can put in a linear increase of wildfires over the past 4 decades. And that's what we did down here, this other additional term, and I'll get to. I want to talk to you for a minute about wildfires because we're going to be talking about wildfires a lot, wherever you are, whoever you are, in the future, in the next few decades. This is a picture from the US West, May through October, area burned as a function since the 80s. I've looked at this data in quite detail from California, very similar. It has this orange is an exponential curve, blue is a linear curve. Any way you slice it, it's doing something like doubling every 20 years, the area burned, which is some proxy for the emissions that are pumped out into the atmosphere from that. This is troubling, to say the least. If I look at California and the warm season only, that doubling time's around 10 years. And I go white, and I'm trying to tell everyone I know that this is going to be a severe problem. We had 2020, everyone remembers that. Literally, it was off the chain, off the charts. And we've had a few years that have been mild, but still very severe if you compare it to 1970, 80 level. So this is going to be something that we can't escape. This is a picture from the Cranston fire in 2018 in California. But what do you think this is most related to? There's a biomass thing, there's forest, the way we've managed the forest, definitely an issue. But what do you think is the main environmental variable that this tracks with? What is that? Thermal something. It's mostly, we found it's linked to the water vapor. This one is vapor pressure deficit, so you just subtract it from the Clausius-Clapeyron equation. It's basically 1 minus relative humidity. The point is, the thing that fire scientists find over and over again is it's most correlated with dryness, atmospheric dryness. And this is why I want to go on this little tangent, because I think it's important for all of us as denizens of the Southwest. Very interesting paper came out this year about how there seems to be a drying tendency that's happening in arid climates all over the world, but this is a case study they did of the Southwest. These are 2 different observational data sets on the left, showing the long-term trend over 41 years of vapor pressure. So that's just amount of water vapor in the air. And you see these big red and yellow patches it's decreasing. This on the right is relative humidity. And relative humidity, remember, is that amount of water vapor divided by the saturation value, that Clausius-Clapeyron, that exponential function in the denominator. And so it's very similar, but the point is that this is decreasing in the observations, the black and gray. But all of our climate models think that, well, you raise the temperature, you should raise evaporation off the oceans and all the forests and everything else, and the water vapor amount should just rise with it. This is why global precipitation is expected to increase in the warming climate. But this idea that the wet regions are going to get wetter and the dry regions are going to get drier seems to be playing out in a way that our models don't fully comprehend. So this to me is extremely important. It's not just global warming. In arid regions, we're globally drying. And that's got to be linked to these wildfires. And that's going to mean we're going to have a hard time in the future, more of a hard time in the future. This is a study of ozone data from actually a graduate from this university. It's blocked here. Malloy took something like 16 years of data and plotted this MDA value for each day of the year and the max and the mean and the minimum. So this is just to show you what the seasonal ozone pattern looks like in your hood, okay? And you see that there's some, and this red dash is that speed limit, that threshold, that air quality standard established by the US EPA. You see that by April, you start to exceed those values. May, it's really kicking up. And June and July are kind of your peaks in general. I tried to line this up. It's not aligned in the y-axis, but the 70 is the same red dashed line. And I got more recent data from the US EPA site of something like a dozen of the worst sites in the region, worst in terms of ozone. And this is what they look like over the past decade. And you see there's no sign of it improving, right? This does not look like we are in a regulatory environment that keeps cranking down on the precursor emissions that are giving rise to the ozone that is the problem. And so this is where I wanted to pause for a second. So this is our analysis. We've done this again all throughout the Southwest, including Texas and California. And these open circles here are, this is the longest time series we have of ozone, the ozone network. And these are in the region around Phoenix. And the red, the solid red symbols are the highest ones in the region. That's design value again each year. And so you see, this is our curve fit from that curve fit of the Phoenix region. This is the stuff that's going to be your design values, whether or not you're in compliance with the Clean Air Act. And this is showing that you are not, and you will not be probably for quite some time. And so this background solution, at least in the year 2000, was about 69. Maybe it's a couple ppb, maybe it's 67 now. Or so we have, you realize that then this background is something we are not controlling and is the lion's share of what's happening in terms of our ozone. Okay, so the green dash fit is just for a fit for all those things, it doesn't matter. And this black line is that sort of background that's superimposed in that fit. Okay, so these are then multiple sites across the Southwest where we've done this partitioning and we further solved for this wildfire contribution, knowing that on all data sets, it looks like it's doubled twice since 1980. It's 4 times larger now than it was area burned on average than it was in 1980. And so we then try to parse this out. Wildfire contributions in this green, increasing linearly, and then this parabolic background. And this bar figure here is just one from 1980, 2020. So every 20 years, just to give you a sense of the progression. Places like Los Angeles, great. Regulatory action has been working, improving. Wildfires aren't really a problem along the coast for the most part because of the ventilation from the Pacific Ocean. But then you get to these other places and you see that Phoenix, for example, you're running into a limit of what you can expect, right? And so we're arguing that the background on wildfires pretty much brings you there and bumps you almost out of compliance get-go. And then there's a bunch of other cities where we did something similar. And then if you take home anything from this, I think, to me, the most important thing is this figure in the upper right, which is our analysis, again, with this simple-minded curve-fitting data from the network that the US EPA operates across the Southwest. And you see that there's this big red and yellow patch in the Southwest. Whereas if you look to the further to the east, you see background levels that are much, much lower and a lot of compliance going on down there. But in the Southwest, we're at this plateau where we're not going to see many more improvements at all. Okay, so I wanted to stop there and just see if there's any questions. And I mean, I'm going to go on for another few minutes. I just wanted to pause on this picture because this is to me the punchline of this talk. And this is what I'm trying to get regulators to acknowledge, and it's not going so well. So, so hopefully, yes, please.
Yeah. So, do you think then the regulatory 70 limit should be moved, or should people just hold their breath for 15 years?
Right. So every 7 or 8 years, the EPA reevaluates all of the health data that's come in about ozone impacts, and they come up with another threshold level, this NAAQS, this ambient air quality standard. That was most recently done in 2015, where they wanted to bring it down to 65, but the Western states said, hey, look, we're screwed if you bring it down to 65. And so they said, 70. I think before that it was 80 or something. So there's, in this process, I haven't shown you this, there's this NAAQS, this black dashed line has been ratcheting down as well. And so we're at a point now where you can't really, right. One of the things I would recommend is if we think about this and we understand some of the root causes for this difference of backgrounds, then we might have a regionally allocated NAAQS or something like that, realizing that, hey, look, the background here is just so high. And in large part, it's because of the stratospheric input, I think, and wildfires. So yeah, that's one suggestion possibly is to do regulations that are regional just because of some sort of geographic imperatives that we all have to live with. Does that answer your question? Didn't even see where it came from. Yeah.
Hello?
Yeah.
So I was going to wait till the end, but you asked, and this is relevant here.
Okay.
In the earlier map of the distribution of ozone around the globe, you did the simulation of your model, and it showed this pulse in the arid part of Africa, so north of South Africa. Yeah, that arid zone in there.
Well, so in South Africa, it's wintertime, which is not the ozone season.
Right. So at some point in this model thing, you see how it gets all light there, right?
Oh yeah, that probably has to do with wildfires. I mean,
really?
agricultural burns.
Oh, okay.
Yeah, huge, massive amount of agricultural burning going on in Central Africa. That's
I was thinking
impacts the climate in lots of ways with black soot and so forth. But I think, yeah, the seasons, again, no one really worries too much about ozone in the wintertime.
Well, it's that big white pulse. And
yeah,
you had the explanation about, which is why the East Coast, there was so little of the moisture in the air. And then I was thinking that was aridity, but I'm trying to understand with the population is pretty sparse down there. So
in Africa?
Well, in that area.
Yeah. My understanding is that there's a massive agricultural burning because it's a huge source of aerosols to the atmosphere. Okay, so I did want to talk about agriculture just briefly. I have a few more minutes. I just wanted to talk about this. I've already talked about the chemistry. This is sort of my classic cartoon comics recap of ozone chemistry. Basically, the ozone and NO are constantly reacting. NO2 is constantly being photolyzed in the daytime. And so there's this photostationary state that's established between those three species. But at the same time, there's also some ozone being photolyzed, which is going to make OH, which is reacting with VOCs, which is then pushing NO to NO2 without consuming an ozone. Because this cycle here is just null. It's ozone reacting with NO, going to NO2. NO2 photolyzes back to ozone. And so nothing happens. But there are these side channels that are slower where you have production of ozone. So NOx, and more we think that as NOx is reduced because of these regulatory efforts, that it's becoming the sort of rate limiting reactant in most places that's most important. So NOx is central to all of this, I think. And so what people have noticed from studies across North America is that there seems to be this plateau in the NOx, in the background NOx. And they've tried to figure it out. What is this due to? We're not sure. A bunch of things have been posited. So I've been looking at a lot of this in California. These are the natural sources of NOx. These are non-internal combustion sources. You've got soil from agriculture. And this is a model for 1 month. But you see that there's significant sources in the agricultural Midwest, which includes Nebraska, and bless you, and California and all of that. Then we see wildfires. This is wildfires changing from last century to this century, increasing. And then lightning is also a natural source. And that has a very, inhomogeneous pattern across the US. Arizona, you got some, but in California, generally not much lightning. So we think that this NOx source is part of this background in those places that are particularly red in this problem, because it turns out when you throw excess nitrogen onto soils, the microbes start to consume it and they leak a bunch of it out. And these denitrification channels produce NO, N2O, which is a greenhouse gas, kind of a separate issue, not chemically reactive in the troposphere, and also nitrous acid, which I think is really underappreciated. And these things depend on how much nitrogen you put down, but in agriculture, most modern agricultural systems, they put down about twice as much nitrogen as the crops need because it's so inexpensive. So what you have is all this excess nitrogen, which is winding up then, I think, aggravating the ozone problem. The main parameters that influence that are, of course, nitrogen amount, soil moisture, and temperature. So let me get you to this part. This is a satellite study we did of California, where you can measure NO2s through ambient sunlight and get a column measurement of NO2 in the troposphere. And this is a picture of the trend for this study we did for about 12 years of NO2 from satellite over California. And what you see is in these urban sites, where most of the monitors are, by the way, right? Because we're interested in exposure to humans. You have these pink and red colors where the NOx is decreasing, again, due to all this regulatory success. But there are large parts of California, including this Central Valley, which is heavily agricultural and has this high ozone background, where you don't have much change. And in fact, you have these remote forests where you have you have an increasing NOx over this period of the study, which was about 12 years. This is just a different way to look at that. This trend in NOx in urban places decreasing like we expect, but in all these other places, it's either plateauing or even increasing. And we think that increasing in the forests are due to wildfires. Again, that's that linear parameter we put in there. And this in between places in rural communities, you're getting some cleanup, but you're also getting some rise, and some of that rise involves the soil source, which we think dominates in agricultural regions. And I just wanted to quickly point out here, this to me is amazing. We took the satellite data from this 12 years of the study and looked at the NO2 and then compared it to surface temperature and binned it with soil moisture from satellite. And what we found was exactly the behavior that people think is occurring in the soil source. That is, it depends on exponentially with temperature until some plateau. And it has this sort of, it was usually modeled as a Poisson function with a peak in the middle for soil moisture. So at really dry conditions, not much NO emitted, and at really wet conditions, not much NO. So the point being that this is just already the column that's in the atmosphere in these regions, the croplands and the forests and the scrublands. And you see it has this behavior with temperature and soil moisture, which seems to indicate that it's being controlled by soils. So I suspect, again, that these soil sources, particularly from industrial agriculture in California and throughout maybe other parts of the West, which are contributing to this ozone problem, this persistent, this stagnation of ozone. And also now we can observe that stagnation in the NOx outside of regions where it was normally measured, which were in urban environments. So just let me leave that with you. If you look at California, you look at temperature, precipitation, and soil moisture, and their trends in the bottom, this is the bottom line. This is the trends per year. Again, California is warming faster than I think anyone is willing to accept at the moment. It's greater than 1 degree Celsius in a decade, right? Since the Industrial Revolution, the whole globe is, what, 1.1 is the IPCC average. California is doing that in a decade. I didn't show you Arizona because it would make you weep. No, I don't know. I actually don't know. And then soil moisture. So we're thinking that, and if I look at agricultural sales of fertilizers, which is the only number you really have is sort of bulk countywide fertilizer sales, you see that that's been increasing about 1% per year. So with more nitrogen being applied and warmer soils, we suspect that this is going to be a very important source of this ozone precursor in the future. And so those are the main points I wanted to get across here, that we think this background, these extreme value backgrounds are dominated in the Southwest by the background. And that's going to make compliance in the future virtually impossible, I should say. And then also we think agriculture is being overlooked. This is something that is not regulated, therefore it would not be seeing those exponential improvements like we use in our simple model. And we think that wildfires are something that we really have to start thinking about very seriously about how to control or mitigate them if we want to keep improving our air quality. And that is all. Thank you so much for your attention. I'm happy to stick around for as long as you want to chat about all of this. I really appreciate it.
Thanks very much, Ian.
Yeah.
We'll have some questions. Usually we like to see if there's some student questions first, but no, go ahead.
Not a student, but
You could be. You look
Yes.
young enough to be a.
so I wanted just to see if I could check my understanding. So during the southern summer, you had a map showing ozone production from, I guess, from surface sources.
This one?
No, it was like a couple slides later. This was
Oh.
northern summer. So yeah.
So let's go to this one, which is a little less noisy.
Yeah, this one. Yeah. So,
Yeah.
so I'm trying to think of, I look at this and it's real, those red blobs are really startling. So the right-hand side is the southern summer, is that right? Am I reading
No, that's our summer. Sorry, that's June, July, August.
June, July, and August?
Which is, sorry, I was focusing on this because this is our ozone season. Remember I showed you how Phoenix ozone goes from
Yeah.
April to about September?
Oh, right, yeah.
So
That's-
this is our ozone season is why I was
see,
focusing
I
on
see.
that.
Okay, so that's
Southern
the-
hemisphere, yeah, I haven't thought about, but
Well,
ready.
so my question is then, since you haven't thought about it, is the western coast of Australia a good analog for the U.S. Southwest? Because look,
right, so that would be the spring would be down here.
yeah.
And the
right, so
western
you get-
coast has this dark blue.
Yeah, so it's an arid, large, stable, arid.
Yeah.
But it doesn't look to be as blooming, as big, and it's less populated.
Yep.
And I think most significantly has a lot less watered agriculture. So I'm wondering
Oh.
if that is a kind of like an A/B test, or is it just not good? Is it not a good enough analog to
Are there big cities there?
yeah, and there's
Canberra?
Perth, and it's about the size of. It's not. It's not. No.
No, there's a no. Yeah, that wouldn't, I don't know where to go with that.
But if your biggest sources are agriculture, not people.
Well, that's my posit on top of this background, which is coming from the stratosphere.
Sure.
Yeah,
there's
mixing
it doesn't
multiple-
mix south to north, so it's just the global south is just not as bad.
Right. So the atmospheric circulation, when you talk about mixing from air in the southern hemisphere to the northern hemisphere, timescale is about 1 to 2 years.
Is the background similar down there, or is it just generally?
The background's lower, actually. Yeah. And it looks like, see, because of you got to realize these are the result of these storm systems and its interaction with, like, for example, the high terrain of the Rockies or the Cordillera of North America, which is propagating up and creating these planetary waves that are helping to create these weather systems that are bringing down this ozone. And I'm not sure that there's the same thing in the southern hemisphere. Yeah.
So there is, to a certain extent, and your Chilean plateau in the southern hemisphere during their spring and summer is also showing the same kind of thing that you're seeing
yeah.
potentially in the Himalayas. So your elevation as part of this background story also makes sense.
Yes, right. And it's an elevation in two ways. So you have arid layers, which give you this strong, deep convective mixing in the atmosphere, but they also generate planetary waves, which propagate upstream and break and help mix down stratospheric air as well. So it's this interesting double dynamical impact.
I think we have a question in the back.
Yeah.
Somebody get the mic.
While we get a mic over there, we have a question from online as well. It says, why isn't the Pacific Northwest affected by poor air quality in a similar manner as the Southwest, given that the Pacific Northwest has high agriculture and frequent wildfires? Fires.
Why is it not?
Yeah. Why isn't the Pacific Northwest affected by poor air quality in a similar way?
Why is it not? That's a great question. We actually did a paper that went up and down the coast from Washington down to the Mexican border. And we find that the background does decrease as you go up. So a couple of things. One of them, if we get back to the stratospheric source, you see that the Pacific Northwest, you're kind of outside of this. You don't have that same impact from the stratospheric inputs because you're just a bit higher north, just because of the dynamics of the atmosphere that's doing this. What's creating this also is this Pacific high pressure system, which rotates the air clockwise and is bringing that upper tropospheric air down to the surface at lower latitudes. So in one sense, the upper Pacific Northwest doesn't have that. You also have, again, these big cities along the coast have a lot of ventilation from the ocean, which really helps them. So San Francisco, even LA to some extent is helped by that. So that would be another reason. And then agriculture, I just haven't studied it enough up there to know if it's anywhere near as large as California. California is the #1 agricultural state in the union. If I look up into the Northwest, this is just a snapshot from a summer, but I don't see a whole lot of soil sources there. And part of this, again, is because what controls it? Temperature. So it's not just any agriculture. It's particularly aggravated by warm, arid climate agriculture, like in the Salton Sea, probably like around here.
Question in the back then.
Yeah, thank you. Thank you for your talk.
Thank you.
The question I have is, what is the coverage of the sensors that measures these zones? Like, what's the coverage like?
Yeah,
why
you
I'm
mean in the
asking
US? That's a good, let's see, I think I have it in this picture. So we tried to put the sensors in those open circles. So we're making an isopleph. So those circles are all the data where we're doing these curve fits and estimating this background. And so those open circles are where the data is. The network, which is primarily controlled by the US EPA in this region of the US.
Okay.
Does that answer your question?
Yeah, that answers the question, because I was looking at the global map and I was thinking that I was expecting some places to have some highs in Africa. And I didn't see that. So I was like, would there be that there's no data or the coverage is not?
Well, we have not done this analysis globally.
Yeah, okay.
We've spent the last several years just doing North America. And so, yeah, you asked me questions about ozone in Africa, and I know very little just because I haven't looked there, but I presume that the network is even less dense there.
Yeah, because if there's no data and there are a couple
Right.
of extrapolations, that there'll be some bias in the.
Yeah. So yeah, I think this is ripe for analysis. We can try to do just about anywhere across the globe, but we have to get people to buy off on it. And it's surprisingly difficult when you don't have this kind of detail like you get from a computer model, which I think gives us some false confidence, in my opinion.
We have a question up here and then over here.
Yeah, please. I can't
So-
really see.
So about the conclusions from the presentation, I
Yeah.
noticed that one of the points was something along the lines of agriculture not being focused on in the discussion of ozone, the atmosphere, if I remember.
Yeah,
Why-
that's also coming from my experience working in California, where this was not received well. Our work on this was not received very well.
Okay. So I wanted to ask, what sort of, based off of what you've seen, do you think like farmer or agriculture in that state receptive, reduced fertilizer consumption or that sort of thing?
Yeah, that's a great point. You would think that's a good angle in, right? Like, why don't we just save money? And I guess my only answer is I think it's just not that expensive. It's not worth their effort. I came across this a while ago. I was doing a lot of methane emissions from natural gas storage and operation facilities. And we thought, no, this work is great for them because what we're finding is leaks and they can pin that down and that's product that they haven't sold, right? And it wasn't really adopted all that well just because it's a pain. It's just like more than it's worth. That sort of couple percent loss that they lose in their pipelines just isn't worth it. But I think, you know, appealing to people's sense of community and who's really suffering from these rural impacts, it's the people who are picking the food, who are out there in the afternoon when the ozone's the highest, you know, that we all really should think about. So I'm trying to come at it from an environmental justice perspective, which I think might motivate people to act more. But you're absolutely right. In principle, if we could get these practices, and again, this was going to require a fair bit of better understanding of exactly what controls those emissions. But we know some of the basics. We can try to implement some of those practices, but we'd have to somehow give them some incentive to do so. Aside from that, because I just don't think it's expensive enough to be prohibited. That's a good point.
One more question, I think.
Thank you so much.
Yeah.
Thanks for that. That was really interesting.
Oh,
And
thanks.
this might seem a little bit offbeat to you, but there's a bunch of us working towards building another space telescope to look for life on other planets.
Great. And
And one of our key biosignatures is ozone. So my question is this: if you were to integrate across the entire globe of the Earth and think about all the sources of ozone, how might you distribute the fractions of each of those sources?
Okay, for other planets.
Well, let's pretend it's Earth. Let's
I
just
love
say
it.
Earth is out there. Let's pretend it's just Earth. Earth with people just like us and industries just like ours. Just out of curiosity, thank you. This is the
So
point.
so
Yeah.
there are people who are doing these detailed computer models who could maybe take a stab at that answer. This is the problem. The NOx, so the VOCs alone are not going to make ozone. So the biosignature of ozone, I've never heard of. I mean, oxygen, of course, that's an obvious one that Jim Lovelock did 50 years ago. But ozone, I'd never heard of. And ozone requires a fair bit of, well, I guess, oh, you mean from oxygen, from a natural
right.
ozone, like the
Yeah, natural
stratosphere.
ozone, right?
Great. Well, that's a really good question. So you might remember this from the 80s that like Ronald Reagan said, trees pollute. You can't just blame industry. Remember that? You read about that? Did your parents ever tell you about it? Your grandparents ever tell you about that? It was very famous. He said this and everyone was like, ha, ha, ha. And he was right though, right? There's a part of it that's right. So the point is like, okay, if you have biosphere creating these biogenics or these volatiles that are going to create ozone, absolutely, but you need the NOx. And so if you look at, for example, these patches are in urban regions, even though I'm suggesting that there's this large background, there's a natural source and all that, but they're aggravated where the NOx is. And NOx doesn't live long. It lives for a few hours in the daytime. So the local production is usually concentrated around industrial places, but you need that NOx. Now, the other source of NOx that's natural is lightning. So if you had a planetary environment that induced lightning somehow, that could produce ozone as well. But you're talking about large scale ozone, like the stratospheric ozone layer.
Yeah, because we're only going to have one pixel. We're not going to be able to resolve.
You're going to have a
everything.
Dobson
So
unit.
you're just going to add it all up. You're going to see one spectral feature, and it's going to be a combination of the sources and the sinks. And the sinks, you talked about photochemistry.
Yep.
We've got that one covered.
Yeah.
We get that one. What I'm trying to understand is, are you telling me that ozone could be a technosignature?
No, I would say, so I can answer your question, 95%.
What? 95%?
is coming from oxygen, which came from the
Okay.
biosphere, right?
Okay, perfect. Thank you.
I mean, plus or minus 100%, but I'm saying 95%. No, you know what I mean. But the point is, the bulk of if you look at a column ozone, 90% of it's in the stratosphere. Most of that's come from photosynthesis.
That's perfect. Thank you.
Yeah.
If we have any more questions, I'm sure that Ian will be happy to answer them up
Yes, I
front
am.
here. So let's thank Dr. Faluna once again for a great talk.
Thank you.
See you all next week.